Hello, my name is Martin Pike and welcome to this lecture from the Ada University course on programming in the large. The subject of this lecture is Ada exceptions, and together we shall complete a series of slides and then you will be assessed on your learning using some quiz questions. A key aspect of programming in Ada is the attention paid to the source code by the Ada compiler and how it treats it like an engineering schematic of program execution. This schematic can be thoroughly checked by the Ada compiler and it will produce warnings and errors if necessary. This is called static checking, but the Ada compiler also inserts code into the resulting program so that runtime errors can be detected that result in an exception being raised. It is also possible for the developer to specify additional checks to take place and for exceptions to be raised explicitly. The point to understand is although runtime errors are mostly unexpected by the developer, the Ada language specification has fixed rules on how they affect program flow. There are several pitfalls that must be looked out for when programming with exceptions. For example, they should certainly not be used to specify normal program flow and should be reserved to indicate exceptional behavior. Falling into this pitfall of using them to specify normal program flow is commonly called programming by exception. Although the impact to the source code is minimal, the runtime performance will be surprisingly impacted by the amount of code that the compiler inserts to raise and propagate the exceptions. If the developer is not careful, and even if they believe they are not programming by exception, it is possible to create spaghetti code that is difficult to statically analyze and far harder to debug. Developers should really be encouraged to use their source code to specify the correct intended behavior of a program, and really exceptions should not routinely be raised. The Ada programming language provides some predefined exceptions that the compiler will check for during compilation and at runtime. The most commonly seen exception is the constraint error, and this is mainly due to the strong typing features of Ada. If a scalar value is out of its specified range, or an array index is out of range, then a constraint error is raised. What differentiates Ada from other programming languages is its ability to raise an exception if a null pointer is dereferenced. This is an invaluable feature in embedded software, particularly when interfacing to hardware or foreign code. In this example code snippet, we see a situation that will lead to a constraint error exception being raised at runtime. The issue is that the value 11 is not within the range specified as acceptable for the array index of the myArray type. It's a pretty obvious error in the source code, and a good Ada compiler will warn the developer during compilation that the exception will unconditionally occur. If the developer ignores the warning, the exception will be raised as soon as a line of code is executed, therefore protecting the remaining program flow from unspecified behavior. The developer is able to describe an exception handler in the source code that includes code to be executed if any exceptions are raised. The handler is placed at the end of a block of statements and starts with the exception keyword and a series of when statements similar to those used in a case statement. Each when statement can handle one or more occurrences of named exceptions, or it can use the when others, which will catch any exception. We present here a code sample showing the comparisons between an Ada exception handler and a C++ try block. This shows exceptions are not unique to Ada, but it was one of the first programming languages to support them. The second sample shows a more complex exception handler that will explicitly run some code if a constraint error or storage error occurs, or a different piece of code for any other type of exception occurrence. The contents of an exception handler commonly include logging an error message or returning variables to known values to ensure subsequent program flow remains predictable. Some care must be taken, though, to ensure the code placed with an exception handler does not raise any exceptions itself. Detecting whether this will happen can be difficult to do statically, so it is safer to keep exception handlers as simple as possible. It's important to remember that exceptions only protect the sequence of statements within a block. Constraint error, for example, is mainly concerned with violations of the specified type model, and therefore these exceptions can occur within the declarative part of a block. Any specified exception handler is only able to handle exceptions raised between the begin and end of a block of statements. Any exceptions raised in a declarative part will be passed to any handler specified in the enclosing frame. For the example, we shall make a call to the procedure P with the argument 0 for its integer parameter v. The first implementation of P on the left-hand side will raise the constraint error in its declarative part at runtime, because x is initialized with 1 divided by v, which in this case is 0. The handler will not be used to handle this exception, as it occurred in the declarative part, so it is still under the control of the enclosing frame. In the right-hand implementation, we see a nested block with an erroneous declarative part. So upon exception occurrence, the handler specified in P will be used to handle the exception, therefore printing out something went wrong. This is a key fact to remember when debugging exceptions, as it can be confusing as to the source of an exception if it occurs in a declarative part. A term used hand in hand with raise when talking about exceptions is propagate, along with exception propagation. When an exception occurs within a frame that has no specified exception handler, the exception occurrence is propagated to the enclosing frame. Propagation continues through each enclosing frame until either an exception handler catches the occurrence and handles it, or there are no more frames at which point the program terminates. In this example, we show a complete context of the call to P with the argument 0. P has an exception handler specified, but we now know the exception in the declarative part of P will be propagated out to the enclosing frame. This means the exception handler specified in P is not yet in scope and is not able to catch the constraint error exception. We are lucky here because the enclosing frame does have a specified exception handler and is written to catch any exception occurrence and to call the text.io procedure put line with a string call to P went wrong. While it is possible to reuse the predefined exception names in your code, to avoid confusion, Ada allows new exceptions to be declared as a specific kind of entity. Here is an example declaration of an exception called myException. It's declared like a constant and has associated scope and obeys the normal visibility rules. The developer is responsible for issuing explicit raise statements for any user-defined exceptions, as the compiler will not insert any code to perform checks for the conditions under which to raise the exception. It is quite common to declare user-defined exceptions when publishing any package specifications for external client use, and to document under which conditions they will be raised. Care, however, must be taken not to go over the top with user-defined exceptions, as their extensive use can fall foul of the pitfalls we have learnt about earlier. It is far better to design APIs around status flags and return values rather than rely on throwing exceptions and demand that the client installs the necessary handlers at the enclosing scope. The raise keyword can also be used in an exception handler to further propagate the exception's occurrence to any enclosing scope's exception handlers. This can be particularly useful if you wish to quickly log an error message about the exception's occurrence and then push the exception onto any enclosing scope. As I suggested in the previous slide, a common pattern when an exception is raised is to log an error message, and with that in mind, the raise keyword supports two separate uses. It is possible to issue the raise keyword followed by the name of the exception entity, including any of the predefined exceptions, or alternatively, a message string can be identified after the exception entity's name. Ada doesn't support any propagation of exceptions accompanied by specific objects, only message strings. There is a particular package provided with Ada called ada.exceptions that gives the developer some useful services to obtain information about an exception occurrence. In the following code snippet, we see an exception handler that catches any exception occurrence and identifies it as E, sort of like a parameter, and then uses E in a call to the exception and score message function from ada.exceptions. This will return any string messages that may have been supplied with the exception entity name when the raise statement was called. We've now reached the end of the slides section of this lecture. You should now have enough knowledge of Ada exceptions to complete a small quiz with questions designed to test your understanding. Each question is marked, and you will have a chance to review your score at the end of the lecture. Good luck! Our first question introduces a procedure called P along with the in-scope ada.textio package. Procedure P has a declarative part that includes a new type declaration of a numeric type called positive that has a range from 0 to 10. A stack object of this new type positive is created, and at initialization it has been set to the value 10. The procedure body immediately increments v by 1 and then calls the putLine procedure from ada.textio. The tick image attribute of the positive type has been provided with the stack object v, which returns the string version of the numeric value. Your question is, what string will putLine output? The answer to this question is nothing will be printed out. This is due to the program flow being interrupted by an occurrence of the constraint error exception caused by attempting to increase v beyond its permitted range. At initialization, it was already set to the last permitted value in the range, and incrementing it within the procedure body is an error. The second question uses an almost identical piece of code to the previous question, however there is a key difference. The difference is that an exception handler has been provided for the block of statements within the procedure P. What output do you think will be produced by this code? The string CE will be printed out. Hopefully you can see why this is, but I will point out just in case you do not. It is the exception handler that caught the constraint error and subsequently called putLine with the string CE. Question 3 presents a slightly more complex procedure called E. E itself has an exception handler for its block of statements that catches any exception, causing the string last chance handler to be printed out. Procedure E has a nested block called myBlock that has a declarative part that declares a stack object A of type positive. There is a single statement within the body of myBlock and another exception handler that specifically catches constraint error and prints out caught it. What output do you think will be produced by this code? This time the code printed out the string caught it, and this was produced by the exception handler in myBlock. The root cause of the exception is myBlock having a statement that assigns a negative number to A which is of type positive. The exception is raised to the myBlock handler as it is the nearest handler of the enclosing scope, causing the string caught it to be displayed. No further action is taken within myBlock, and the program flow returns to the remaining statements of procedure E. We reuse the code from the previous question now, but with a subtle change to the exception handler declared in myblock. After the string caught it has been output, there is a raise statement. What output do you think will be produced by this modified code? The value printed out was the string caught it, followed by the string last chance handler. This was as a direct result of including the raise statement at the end of the exception handler defined within myblock. This has the effect of further propagating the exception to any handlers in the enclosing block, that here being the exception handler defined in the procedure E. We continue to use the same example code snippet, except now a change has been made to the declarative part of myblock. The declaration of A has an initialization value of -1. Note the raise statement has been removed from the exception handler declared in myblock. What value do you think will be printed out by this code? Here you can see the change was to induce a constraint error exception in the declarative part of myblock by assigning an illegal initial value to A. The exception handler defined in the body of myblock is not yet in scope, so the exception is propagated to any handler in the enclosing scope. The procedure E has declared an exception handler that prints out last chance handler. Question 6 is going to test your knowledge of exceptions being raised by conditional expressions as opposed to assignment statements. We use a slightly different code example here that defines a block with an exception handler that will catch any exceptions and print out the string exception. The block's declarative part declares two stack objects, and the body assigns 0 and 5 to those objects respectively. We then meet a conditional expression that, if true, will cause the letter A to be printed out. Alternatively, if the conditional expression evaluates to false, the string division by 0 will be output. Take a walk through the code and decide what value you think will be printed out. The answer is the string exception was displayed. If you take a look at the conditional expression, the evaluation of the right-hand operand involves dividing B by A, which results in 5 being divided by 0, raising a constraint error exception. This example hopefully demonstrates that it is possible for exceptions to be raised by conditional expressions as well as assignments. Hopefully your compiler will have warned of this exception during compilation. Now we move on to an example that tests your knowledge of ADA scoping and visibility of user-defined exceptions. In this example, we have defined a package P with a provided interface that includes a procedure named call. Within the package body of P, there is the implementation of call that explicitly raises a user-defined exception named myException. Our main procedure names P in a with clause to use its provided interface and defines an exception handler for myException. Is this code correct? Click on the tick icon if you believe the code is correct, or the location of the code you suspect is wrong to see if you are right. The code is incorrect, and the main procedure would not have cleanly compiled. MyException is not visible from main because it was declared within the package body of P. The declaration of myException should have been moved to the package specification of P in order for this code to have compiled. This demonstrates that user-defined exceptions are subject to the same naming and visibility rules as any other user-defined Ada entity. Question 8 introduces a package specification for P that includes a procedure named call. The package body of P has a user-defined exception called myException, and the only statement in the body of call is to raise myException. The procedure main declares a stack object C that it uses as a loop index. The loop includes a nested block that has an exception handler declared that does nothing. The body of the block includes a call to the procedure call from package P and an increment of the loop index C. Click on the tick icon if you believe the code is correct or the location of the code you suspect is wrong to see if you are right. In this case, the code is incorrect. The exception explicitly raised by call will propagate to the handler defined within nested block. The program flow is therefore directed around the incrementing of C, and therefore the loop invariant is always true. This will result in the loop never exiting and is therefore an infinite loop. This is an example of how difficult it can be to spot runtime errors involving exceptions just by code inspection. The program flow can be seriously compromised by exception propagation, and in particular the contents of exception handlers. Our next question will test your understanding about the type of code that can be placed in exception handlers themselves. Remember that raising exceptions is equivalent to an invisible goto statement from some point in normal program flow to the exception handler. The handler must be aware of the context in which it can be jumped to, and it must behave correctly. Here we are presented with a package P that declares an array type called atype and with an integer range and integer components. There is a function called safeget that accepts an object of the array type, an index, and it will return the integer component at that index. The package body shows that there is an exception handler in the implementation of safeget. Click on the tick icon if you believe this code is correct or the location of the code you suspect is wrong to see if you are right. You were correct if you suspected the code was wrong. While the body of safeget contains a return statement, the locally scoped exception handler does not. If an exception occurred within the body of safeget, then it would be propagated to the locally scoped handler that itself may lead to a program error exception at runtime due to the missing return statement. Hopefully your compiler will have warned of this exception during compilation. We now arrive at the last question in the quiz, and a slightly tricky one. In the procedure main, we have declared a new record type called R that has a single field called F of the type positive, which is defaulted to -1. A stack object of the record type is created as V, and it is initialized using an aggregate assignment that sets the field F to 1. The code continues on to call putLine from the ada.txt.io package and uses the tick image attribute of the field F within the stack object V. Click on the tick icon if you believe the code is correct or the location of the code you suspect is wrong to see if you are right. Although a tricky question, hopefully you got this answer correct. This code is fine, because the explicit initialization of the field f within the v instance of R using the aggregate assignment overrides the default invalid value. Therefore, no constraint error is raised. Thank you for attending this lecture on exceptions as part of the course of Programming in the Large using Ada. Together, we have covered the different types of predefined exceptions provided by the Ada language, how they are used, and how to handle them correctly. I hope you have found it a valuable step in learning the Ada programming language, and that you continue on to the other lectures in this course from the Ada University. Thank you.